Today's lesson is an extension of the first lesson on stoichiometry we did, where we learned about the mole ratio, which are the coefficients, right? And how to use them as a conversion factor to convert back and forth between moles of one thing in a chemical reaction into moles of another. And today we're going to learn how to add some more conversion steps onto this to incorporate mass as a possible given unit or a possible unit that I'm asked to solve for. Okay. So remember, you guys, all stoichiometry problems start with a balanced chemical equation, right? Because all stoichiometry problems go through that mole ratio, which the mole ratio are the coefficients. All right, so we focused on this last time, a single step, baby step stoichiometry conversion where I give you something given in moles and I ask you to find something in moles. I use the mole ratio, right, to get through that step, to go across my dotted line, to escape my green go section, right, where I'm starting, and to get to where I am stopping my red light section, okay? So what we're gonna add on to today is, boom, this. Okay, so we did this middle section last time. Okay, using the mole ratio to go from a given moles to an end moles, right? But what if I give you something in grams and then ask you some information about another guy? Well, I can't just apply my mole ratio first. I have to get 2 moles of my given first, and then I can use my mole ratio, and then I'm off to the races and I'm dealing with somebody else in the chemical equation. They're like, well, how do I get to moles from grams? Guys, we've done this conversion before. Grams to moles of the same thing. It's just going to be using the molar mass of that thing, right? That substance, which means I will be applying, according to the periodic table, however many grams of that substance are in every 1 mole of that substance. So let's pretend if I ask you to figure out the grams of your ending substance, meaning I'm not stopping at moles, not stopping after the mole ratio. Well, I can extend that out and be like, I can just use the molar mass of my ending substance, right? Oriented in a way that I can then use it to convert for grams. That is all we are doing here. So by the end of today's lesson, you guys will be able to go from molar mass, mole ratio, molar mass. What if I ask you to take it from grams of a given to grams of an unknown, which is really cool. So let's bounce down here and we are going to go strictly to my document camera. Okay. Obviously for today's lesson, I'm going to be using my reds and greens again because that was so super duper helpful last time. I'm going to be using my calculator, and you will need your periodic table handy because we're going to use molar masses. Y'all are like, oh my gosh, this chemistry thing, it all builds on itself. Yes, it does. Yes, it does. So as a review, we were messing with this last time, the little mole ratio. Now all I have done is I have added a little bit more to my stoichiometry math with some more options of where I can start with and where I can end. Okay, so how to do mole to mass problems. A mole to mass problem, and in fact, I'm going to I have a separate one of these that I think may be easier than me moving up and down every single time. So moles to mass problems, that would be where I am starting you at moles, but I'm asking you to go to mass of your unknown. If I'm starting here and I'm ending here, it is a 2-step process. The first step is using the mole ratio, and then the second step is using the molar mass of my ending substance. So let's check it out. So it's gonna look something like this, right? I have my moles of my given, mole ratio is up first, and then molar mass is second. Okay. But all stoichiometry needs a balanced chemical equation. I've provided the chemical equation on this first example. You are happy for that, but it does need to be balanced, okay? So I have iron reacting with oxygen to produce iron 2 oxide. This is a synthesis reaction, okay? It is not balanced because I have 2 oxygens on this side and only 1 on this side. So I got to put a 2 in front of the iron 2 oxide, right? Which means I need to put a 2 in front of my iron on the other side. Balanced? Okay, now I'm ready for the stoichiometry. Get your green to represent what value or what given I'm starting you off with, and get your red to represent what I'm asking you to solve for. Okay, so remember, we find our given by the number. I have 20.8, what? 20.8 moles. That is important information for me. And then moles of who? Who did I give you moles about here? Of oxygen. Find oxygen in your chemical equation, and underneath oxygen, write what your given information was. I have 20.8 moles. Okay, so that's where I'm starting. And I can also circle the number, the coefficient in front of oxygen, because that is the number that I'm going to be using for that mole ratio step. That every stoichiometry problem has one when you get to it. Okay, what I'm asking you to solve for, how many who? How many grams? And grams of who? Oh, iron 2 oxide. Oh, well, where's iron 2 oxide? He's right there, right? So I'm going to write what it is I'm trying to solve for, and it's grams, so I'm going to write question mark grams. Now those words do not mean anything to me. What I have written underneath my reaction equation is all I need to know. I can totally see I'm starting with 20.8 moles of oxygen, and I'm ending with grams of iron 2 oxide. And in fact, that will require me needing to use the mole ratio to get over there. So I have circled the number in front of the iron 2 oxide also. So it will be a 2-to-1 ratio when I get there. Anyway, so this is a two-step process. I set up my train tracks. And guys, just like last unit when we did very simple molar conversions, you may not in your brain know how many steps something is, but you'll learn to get to the point where you're depending on your units and your ability to cancel things off on top and on bottom to kind of guide you through where you're trying to get to from these problems. Okay, so my given always writes right there, is always written right there. I have 20.8 moles of who? Of oxygen. Okay. Well, I'm already at moles of oxygen. Y'all, I am immediately ready. Once you are at moles of your given, it is time to jump over the dotted line and apply your mole ratio to stop talking about oxygen and start talking about iron 2 oxide. Okay, so that means mole ratio time, which says there is a 1 mole of oxygen for every 2 moles of iron 2 oxide. Okay, and I know I have set that up correctly because I can cross off moles of oxygen, moles of oxygen. Now you see why it makes a difference whether it's of oxygen or iron 2 oxide, because I want to make sure that the units are associated correctly. Okay, but we didn't want to stop at moles. We wanted to stop where? Grams. Well, that just requires me doing a final conversion to convert from moles of iron 2 oxide to grams of iron 2 oxide. Moles of one thing to moles of the same thing. That is just me dealing with all red stuff from here on out, applying the molar mass of iron 2 oxide to this last conversion. So that means I need molar mass to on my periodic table, but I do know that I can anticipate what units are going to go on the bottom. I need to see moles of FeO on the bottom, right? Which means I'm going to see grams of FeO on the top, okay? We know in a molar mass, it is a certain amount of grams in every 1 mole. So molar mass will always have 1 in front of the mole, right? And on the opposite side of the conversion factor will be the decimal number from the periodic table. So I can find iron and I can find oxygen. Where's iron? Where's iron? Where's iron? He is here, 55.85. According to my formula, I have 1 of him. So I go 55.85 plus, and I have, who's next? Oxygen. Only 1 oxygen. Oxygen's molar mass is 16. Okay, so I have 71.85 grams of FeO in every 1 mole of FeO. So that is what I will write in here, 71.85 grams, okay? I know I've set it up correctly because, look, I can do this. Boom, boom. Yes? So where you see this split from going from green to, should be red, it's like a dark pink, is where I am jumping over the line, which means I am done talking about my given substance and I'm now talking about the substance that you are going to solve for information for me for. Okay, so now I'm ready with the calculator. And the math that I do is I multiply everything on the top together, and if there's anything of significance on the bottom, I divide it by the bottom. So I have 20.8 times 2 times 71.85. And that gives me this big old fat number. I'm going to write that full number here just so we can look at it on our page, and then we can, round it to the appropriate number of sig figs. Okay. How many sig figs am I going to round this answer to? Well, it depends on how many sig figs are in the number in the problem. 20.8, that is 3 sig figs for us. That means I need to round my answer to 3 sig figs. So I want that guy, I want that guy, and I want that guy. Everybody else I do not care about, but I want to be careful. I want to make sure that I do not write just 2, 9, 9 and be like, amazing, I knew how to round that last 8 up to 9 because I know, and that is the right answer. No, this was like a 2,000-ish number. A 2,000-ish number cannot be rounded to, oh, that's like the same thing as 200. No, make sure that you keep everybody in the correct place. By me adding a 0 does not change the sig figs unless I put a decimal in the number. So we are good there. That still has 3 sig figs, but what I am missing is the units. Grams. And of who? Iron oxide. So this is the correct answer. Noticing that in my dimensional analysis, I have units, and I have of what, whether it is oxygen or iron oxide, okay? When I'm doing all of that work, first of all, you will get credit, because if you don't show that work, you're getting no credit from me. But when I take the time to do all of that, I am actually doing myself a favor, because I'm not going to get lost. I'm not going to get to this point at the end and be like, what? Of who? You know, it's the last things that you have not canceled off. Okay. So these are moles to mass problems. They are 2 steps. It says, now try problems number 1 and number 2. And you were like, what is she talking about with problems number 1 and number 2? Well, you have a practice assignment worksheet here. The practice assignment, in fact, it's a 2-page or 4 pages, 2-page front and back, of where I have you do more of these practices, okay? The first few sections are actually organized to where we are enforcing, I'm telling you what strategy you're implementing, and then the remainder of the practice is all a mixtape of sorts where you have to figure out where are you starting from and where you're trying to get to. That was a lot of words. Okay, so anyway, we are ready now. It says we are going to problem number 1. These are all moles to mass problems, exactly like the problems that we just practiced together. Okay, I don't care about the words. I see an equation. I know I need to balance this chemical equation. So we are ready to go. Boom, 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 boom. We've seen this problem before. 3 oxygens and 2 oxygens. I double the 3 side, which then means I have a 2 here in front of my potassium chloride, which then means I need a 3 in front of my O2 here. All right, so I had to do all that work first. Now I'm ready with my colors. I'm ready to see. Ready to see. I have so many papers here. It's like a little bit chaotic today, but we are fine. Okay, it says if 5 moles, so that's my given, of O2 were produced, that number of oxygen goes underneath the oxygen. I'm going to write 5 moles. Yes? And then I'm asking you to find out what? Grams. How many grams of who? Potassium chlorate. So potassium chlorate's there. I'm going to put a question mark, grams. That way I have it visualized. I'm like, I'm starting already at moles, which is good. And then I'm going to have to take it all the way to grams. So this is a 2-step process like we just practiced. Okay, I'm going to make that a little bit longer because these stoichiometry problems require a little bit more words, you know. Okay, so my given was 3 moles of O2. And you're like, well, what's next? Well, you are at moles of your given. That means I need to go to my mole ratio step, which is going to tell me there's a certain amount of moles of O2 for every, I'm crossing the dotted line here, I'm crossing the dotted line here. So the next thing I'm going to write is in red, is in red, is in red. Well, my red guy is potassium chlorate. I need to know how many moles of potassium chlorate there are, right? Well, how do I figure out that stuff? Well, it's the numbers in front of those substances in the balanced chemical equation. There's 3 here, and there is a 2 here. So I'm starting with moles. I apply my mole ratio, so I can go boom, boom. Yes? Now I am here. I have jumped over that dotted line. I'm like, woo, we are at in moles. I stopped there, but no, you do not stop. You've written this underneath your equation, so you do not forget where you're trying to get to. I'm trying to get all the way to grams, which means I need a final step here, implementing the molar mass of potassium chlorate to calculate how many grams that would be. Well, molar mass is always in every 1 mole of the substance this time being potassium chlorate. There's a certain amount of grams. Yes? Notice that everything that's in red here is of the same thing, not oxygen anymore. Nope, this is all dealing with the same guy, potassium chloride. Okay. How am I supposed to do that? Periodic table. Mine flew away. It is all the way over here. Oh my goodness. I told you today is chaos. It is chaos today. All right, so I'm ready. So I have potassium chlorate, which means I have 1 potassium. Y'all are just going to have to trust and believe at this point you know how to solve for molar mass. I'm grabbing these the decimal numbers from the periodic table, right? So potassium's molar mass is 39.1, right? And I have 1 potassium. Then I have chlorine, so plus 35.45 is his molar mass, and I only have 1 of him. And then I have oxygen. Oxygen's molar mass is 16, and there are 3 oxygens, so times 3. So the overall molar mass of potassium chlorate is 122.55. 122.55 grams in every 1 mole. And I did not write it in red. I will go back and trace because that's going to drive me crazy. Okay, cool. Amazing. So the purpose of this was I was able to now be like, okay, no more moles of potassium chlorate. How many grams is that amount of moles of potassium chlorate? So now I'm excited. I'm ready to grab my calculator. I'm ready to do the math. I go 3 times 2 times 122.55 equals, and then if there's anything on the bottom, I divide it by the bottom. There's a 3, so I go divided by 3. Amazing. I get 245.1. That's my answer, but what I've got to do is I've got to make sure I round it to the correct number of sig figs. You guys are not ready for this one. Wow, how many sig figs are in this number? That's just 1. Uh-oh. So rounding this to 1 sig fig, I just need that 2. Do I need to round that 2 up? I do not. This is a wackadoo. Wait, I do something wrong. I know what I did wrong, you guys. What is happening here? I wrote 5 moles here, and I wrote 3 moles here. I do not know what my brain was doing with this transition, but this given, sorry about you guys, should have been a 5. Now, that sets me off a little bit better. I was like, what is going on with me today? So I have 5 times 2 times 122.55 equals, and then I'm going to divide by the 3 that I see on the bottom. So I get 408.5. Right? So my answer, though, it was not 200 and something, it's 408. I need it 1 sig fig. So that means that I need the 4. I do not need to round that 4 up, but I'm not going to call my answer 4. That is 400. So I got to make sure that that 4 is still in the hundreds place, but I put zeros at the end to hold place. Do not put a decimal. And the units for this are the only thing I haven't canceled off, which is grams of potassium chlorate. Amazing. Cool. Okay, so we're going to do one more problem with this strategy of given moles and ending in grams, and then we're going to go back to our notes handout and see what other options there are for us. Okay, so we're excited. How many grams of potassium chloride? Oh, you're like, wait a second. Where's the chemical reaction for me to balance? Oh, no, you got to write it yourself. So switch your brain, ignore the stoichiometry. We need to produce a chemical reaction equation. So what are the reactants? What are the reactants? How many grams of potassium chloride is produced from 2.5 moles of potassium and excess chlorine gas? So the first chemical that you see may not be your reactant, so you do have to do some thinking here. I'm sorry. It says how many grams of potassium chloride are produced. So I'm producing potassium chloride from 2.5 moles of, here are my reactants, potassium and chlorine. Potassium and chlorine. Potassium and chlorine. I'm going to write those down. Potassium symbol is K. He is not a Hofbrinkel, so that is what potassium looks like. And then chlorine is my second reactant. He is Cl, but he is diatomic Hofbrinkel, so he gets a 2. So even if I didn't tell you in words that you're making potassium chloride, you could look at these 2 things and be like, there is no other option for me except for to take these 2 single people and combine them together to make a couple. So this is a synthesis reaction, which is going to require me to ignore the subscripts and make a compound between potassium and chloride from scratch, depending on what their charges are, depending on their group on the periodic table. So potassium's group 1, he's got a +1. Chlorine is group 17, he's got a -1 charge. So the ratio of those 2 elements to each other when they make an ionic compound is a 1-to-1. I have KCl. And then we balance, which means I need to put a 2 here and then a 2 here. We feel good about that. Awesome. Okay, so now we are ready to do the stoichiometry of it all. So I get out my green and my red. My given is 2.5 moles of who? Potassium. Here's potassium. I write 2.5, and I'm going to write the 0 because that 0 is important. And now hopefully I won't make a mistake because hopefully that number will end up where it needs to go down here when I do my train tracks. Hopefully, we'll see. And then I have, where am I going to? How many grams? I'm going to grams of who? Potassium chloride. Well, which one is potassium chloride? Him, question mark, grams. I also see the numbers that I will be using for my mole ratio, right? Okay, here we go. I'm ready to crank through now. So we'll write our given here. Our given is 2.50 moles of potassium. I'm already at moles of my green thing. I'm ready for the mole ratio time. I'm ready to implement the 2 moles to add 2 moles for my mole ratio. So there are 2 moles of potassium. This is where I'm switching colors. I'm now not talking about potassium anymore. I'm talking about potassium chloride for every 2 moles of potassium chloride, right? Boom, boom. Well, I don't want you to end at moles. If I wanted to end at moles, that would be great. I'd do my math. I want you to take it to grams. Oh, okay, so I need one more step. That is fine. We can do the hard things. Well, the next step is the molar mass of potassium chloride, which says the molar mass of every 1 mole of potassium chloride, there is a certain amount of grams of potassium chloride. So I type in my calculator, grab that molar mass. I got 1 potassium. We said potassium's molar mass individually is 39.1. And I have 1. And then I have 1 chlorine, whose molar mass is 35.45. So the total molar mass of potassium chloride is 74.55. Amazing. So this step is going to allow for me to get out of moles territory and take it all the way to grams. So I'm leaving moles and I'm all the way extending it to grams. Okay, so I'm typing in my calculator. I got 2.5 times 2 times 74.55. And then I divide by 2. And if you want, you can be smart and just realize that those are ones there anyway. But if you were like, no, I want to follow this strategy, I understand. I'm right there with you. Anyway, so this is my answer. I have sig figs I need to take care of. How many sig figs are in this number? 3. That ending 0 is significant because there is a decimal in the number, which means I need 3 sig figs from this number. So my final answer is 186. What are the units? Grams of who? Potassium chloride. Okay? Cl. Boom. All right. I love that. Okay, get back out your notes page. So put away the practice for a little bit right now. We're going to do the next section on how to do mass from grams to mole problems. These are also 2-step problems, okay? Where my given is going to be in grams. I didn't mean to cross that out. I meant to underline that. You guys understand. Well, if I'm starting all the way over here at grams and not at moles, my first step is an all green step using the molar mass of whoever the green thing is. So the molar mass of my starting guy A over 1 mole of A. And then if I'm taking it to moles of my ending guy, moles to moles is my mole ratio. That's the first step where I see a change in color of sorts, right? So my mole ratio will be my last step. Okay, let's jump right into the problem. The first thing I see is like there is a chemical equation for me that I need to balance before I'm allowed to go further. Okay, so it says, y'all, I think this is the exact same equation as the one before that we did for our practice example in our notes page. It is. So you may rebalance it again. So we are balanced. We have our balanced chemical equation. We are ready to find our given. There's the number 50. But 50 what? Grams. Of who? Iron. Where's iron? There he is. I'm going to write the given underneath here. I got 50 grams of iron. Woo! There you go. I love that. That 2 is going to be my mole ratio guy. Where am I trying to take it to? Moles. So I'm ending at moles. Of who? Iron 2 oxide. So I'm going question mark, moles. And I know I'll need to use that too for my mole ratio step. Okay, she's telling me this is 2 steps, and I'm like, I'm ready to map it out, but I'm going to see how we can make our units make this make sense for us. So here's my given. My given is 50 grams of who? Fe. We want to use the mole ratio, but we are not ready to use the mole ratio yet, because if we need to use the mole ratio, we need to be at moles of iron. I am not at moles. I'm still back here at grams. Well, how do I get to moles? I just use the molar mass of iron like I've been doing for a while now, right? Which states there's a certain amount of grams of iron for every 1 mole of iron. Noticing that I'm putting the grams on bottom down here so I can cancel off. Well, what is the molar mass of iron according to my periodic table? It is 55.85, right? So this step has gotten me 2 moles. I am now here. Well, I need to get 2 moles of FeO. That's fine. I'm just going to do the mole ratio now, okay? Which then means I look at the coefficients, right? It is a 2-to-2 ratio, which is the same thing as a 1-to-1, but I will write the 2s because that reminds you that you know where these numbers came from. So for every 2 moles of iron, I have 2 moles of FeO. Amazing. So those now cancel off. I'm good. I grab my calculator. Am I good? I don't know. Am I ever really good? We try sometimes, don't we? Okay, 50 times 2 equals, and then I divide by what's on the bottom, divided by 55.85, and then divided by 2. I get 0.8955. Okay, how many sig figs, how many sig figs, how many sig figs am I given? You're going to love this. Does that trailing 0 count? No, because there is not a decimal in the number. This is only 1 sig fig. So I need to grab only 1 sig fig from this number. Leading zeros are never important, so you can skip right over him. He does not count. My first sig fig is that 8, and I do need to round that 8 up to a 9. And so that is my correct answer with 1 sig. What are the units? Moles of FeO. And I didn't write that in red, but that's okay. You guys get it. FeO. My OCD brain is like, I cannot leave that not on red. Okay, so let's bounce down. It says now try problems 3 and 4 from our practice. So we will now be trying problems 3 and 4 from our practice. Okay, so problems 3 and 4, those will just be like the problems that we just did. Okay, the first one, I don't care about those words. I care about balancing my equation because I know that that is important to me. So my first equation is I got this business. N2O5 plus water leads to nitric acid. So to balance this guy, it looks like all I have to do is to put a 2 there, and then everybody looks pretty good to me. That is amazing. Now I am ready to figure out what it is they're asking me to solve for. How many moles of nitric acid will be produced when? Here's my number. 0.65 grams of N2O5 react. So that would be called dinitrogen pentoxide, this covalent compound. We get to use our dis, tris, tetras, etc. So 0.65 grams of that guy. Boom, 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 boom. So underneath here, I write 0.65 grams. So it lets me know my given is in grams. Well, where are they asking us to take it to? I'm asking you to take it to moles of nitric acid. Where is nitric acid? There he is. I do a question mark. Moles. So right away I know I'm going from grams to moles. Right away I know my given is not here at moles, it's at grams. And when I cross that line, I am stopping not at grams, but I'm stopping here at moles. Okay, so let's see if we can accomplish this. My given is 0.65 grams of dinitrogen pentoxide. Where am I going next? Well, I see grams. I gotta see grams down here, and I'm nowhere near moles, right? This part is to get me to moles. So, molar mass time. There's a certain amount of grams of dinitrogen pentoxide in every mole of dinitrogen pentoxide. So I grab my periodic table. I am ready to molar mass time for him. I have 14.01 nitrogen. There's 2 of them, so times 2. And then my next element is oxygen. He is always 6, and I have 5 of him. So my molar mass of this entire beefy old guy is 108.02. Cool. And so the purpose of that was for me to go boom, boom, out of there. So now I'm at moles of my given. We're ready to cross over the dotted line. We're ready for a mole ratio time. Woo woo. Okay, mole ratio time, which means, oh my gosh, my coefficients. Look at this. It is a 1-to-2 ratio. But I need to write my given on the bottom, my 1 mole of N2O5, and then my finder where I'm ending on the top, 1 mole of nitric acid. because then I can go boom, boom. And then I stop there because that's where they asked me to stop. Do not take this to grams. They told you to give you moles. You stop there. Okay, I'm excited. Let's go ahead and calculate it up. All right, I got 0.65 times 2 equals, and then I divide it by 108.02, and I get, all right, that number, very small number, but how many sig figs do I need? 2 sig figs in that problem, which means my answer needs to be 2 sig figs. None of those leading zeros count. My first sig fig is the 1, and I only need another one, which gives me a 2. What are the units? Moles. And of who? HNO3. All right, amazing. One more problem, and then we'll go back to the notes to finish off with our last type of mass stoichiometry problems. There's not a chemical equation. Well, I gotta figure out what chemical equation I'm gonna write. Hopefully from this information, I can at least get the reactants. When 9.334 grams of zinc reacts with excess hydrochloric acid. Okay, I mean, they tell me what one of my products is, but I can, as long as I have the reactants, I can produce the rest of the chemical equation. My first reactant is zinc. My second is hydrochloric acid. Boom, zinc. He is not Hofbrinkel, so he does not get a subscript of 2. And they gave you the formula for hydrochloric acid, so that is quite nice for us. This is a single replacement reaction where zinc will be kicking out the hydrogen cation to make a new compound. So that means hydrogen is one of my products by himself. But when he is single, he looks like that unless he's diatomic, which he gets a 2. And then my formula for my other guy that's zinc's going to make with chlorine, I got to keep in mind zinc has a +2 charge, right? So my formula for zinc chloride is ZnCl2. Then the balancing of it all, we are ready to balance to make sure that this equation makes sense. All I have to do is put a 2 in front of my hydrochloric acid. Okay, now I'm ready for my reds and greens. My reds and greens, what did they give me? They gave me 9.34 grams of who? Of who? Zinc. So I write underneath here 9.34 grams. And I know that when I get to the mole ratio step, I'll be using that 1 in front. Where am I trying to take it to? Where am I trying to take it to? Moles of who? Zinc chloride. Where's zinc chloride? There he is. So underneath him, I'm going to write question mark moles. I know I'll need that for my mole ratio. Okay, so we are ready to go. We are ready to blast out my given, right? My given is 9.34 grams of who? Zinc. Mole mass, our molar mass time to get from grams to moles, which means I'm going to have a certain amount of grams of zinc for every 1 mole of zinc. Yes? Well, I grab my periodic table, and according to my periodic table, it looks like the molar mass of zinc is 65.38 grams in every 1 mole. And I've set that up correctly because I can cancel off grams of zinc with grams of zinc. So now I'm at moles. I've made it to moles. We are ready for mole ratio time. Well, what's the ratio between zinc and the zinc chloride that I'm trying to take it to? It's a 1-to-1 ratio. Kind of boring, but important. So 1 mole of zinc. And now I'm taking it to zinc chloride with my mole ratio. So I'm switching colors. So for every 1 mole of zinc, there is 1 mole of zinc chloride. Cancel off on top and on bottom. I'm ready to mathy math. Okay. We have 9.34 times, not times. The only thing I have besides ones is on here is that molar mass, which is on the bottom. So I go divided by 65.38 on the bottom. So my answer is this. How many sig figs do I need? I need 3 sig figs because my given is 3 sig figs. So my answer is 0.143. Keeping in mind that leading zeros are never important, never significant. And the units are moles, and of who is ZnCl2. Cool. Okay. All right, let's get back to our notes. I feel like we're bouncing around all over the place, and that is okay. We have one more type of mass stoichiometry problem to tackle. And these are the problems that go from mass of one thing to mass of the other thing. We are going all the way across our stoichiometry map. So it's going to be 1 step, 2 step, 3 step. First one being the molar mass. Second one being your mole ratio, the coefficients, and then the third step being the molar mass of your ending substance. Okay, so let's kind of map that out with our colors if you would like to. So here's my A. My A is all green. That's my starting substance. That first step is all green, right? Because that's the molar mass of just A. The middle step is where I get the splits. That's my mole ratio. It's where I jump over the dotted line. But the last step is all pink or all red because that is where I'm ending, okay? So now we're ready to go. I'm excited. So balanced equation. This is the same balanced equation that we've seen before. We'll go ahead and balance it by putting 2's. Now I'm ready to read the problem. My given is they've started me off at 8.8 grams of oxygen. Here is oxygen, right? 8.8 grams underneath him. So I'm starting at grams. Where am I taking it to? Where am I taking it to? Grams of who? Iron. There's iron. Question mark, grams. Looks like I'm going from grams of my given to grams of my ending. I will be going all the way across this mole map. It's a stoichiometry map now, right? And it will be a 3-step process, right? I feel like I may not have a lot of room here. This may be kind of sneaky. Where this first section will be my molar mass. This section here will be my mole ratio. And this section here will be the molar mass of the second guy. Okay, so let's start putting this in place. My given is 8.8 grams of oxygen. Well, to get anywhere close to talking about the other guy, talking about iron, I got to convert this grams of oxygen into moles of oxygen. So the molar mass of oxygen is a certain amount of grams in every 1 mole of oxygen. So molar mass of 1 oxygen is 16 according to the periodic table. Of 2 oxygens here is going to be 32, right? And I do that so I can go bam, bam. So we are now at moles of my given. Well, that means the next step is that I can now get to moles of my iron. I utilize my mole ratio, which says for every 2 moles of iron, there is 1 mole of oxygen. So I put the 1 mole of oxygen down here on the bottom, and then the 2 moles of iron on top, so I can go like this. Boom, boom. Yes? We're not done. I don't want you to stop at moles. If I wanted you to stop at moles, that sounds great. You stop there. But I'm telling you to take it to grams. Not a big deal. Moles of iron to grams of iron, just use the molar mass of iron, which means I am all red from here on out. The molar mass, it says for every 1 mole, you have a certain amount of grams. So for every 1 mole of iron, I have a certain amount of grams of iron. And these are easy molar masses. Luckily, they're just single elements from the periodic table, which we love. So the molar mass of iron is 55.85 grams for every 1 mole. So I do that because now I can cross off moles of iron. So this is me going from grams to moles, jumping over the dotted line to go from moles to moles using the mole ratio, and then finally going from moles to grams using the molar mass. So these problems are kind of super satisfying. I'm talking and I have not solved my answer. Let's see if we can do that. Here we go. We have 8.8 times 2 times 55.85, and then we're going to divide that by 32. Amazing. Okay, so that's my answer. I need to round it to the appropriate number of sig figs. That number in the problem, that 8.8, has 2 sig figs, so my answer needs to be rounded to 2 sig figs. I'm running out of space. That is okay. I have 31, and the units are grams of who? Iron. Wonderful. Okay. All right. Let's bounce back to our practice and see if we can tackle some of these problems. Mass to mass problems. How exciting for us. Okay, let me get all my things organized. There's so many things that I'm going on over here. Okay, got my periodic table, got my calculator. I'm going to sit crisscross applesauce because I'm getting excited now. All right, Balanced equation. Focus on you first. She gave me an equation. It is not balanced, so I'm going to do that first. So I have H2 plus oxygen, or hydrogen plus oxygen creates water. So this is a synthesis reaction for water. I know I need to balance my oxygens by putting a 2 in front of water, which means now I need to fix my hydrogens by putting a 2 in front of hydrogen. Cool. So that is balanced. We are ready for my reds and my greens. My given, my green, it says how many grams of water are produced when 2.50 grams of oxygen are used. My given, 2.50 grams of who? Oxygen. Where's oxygen? Here. Write my given 2.50 what? G. Important. Also, that's going to be important down the line. What am I asking you to solve for? I'm asking you to solve for grams of who? Water. Where's water? There he is. Right. Question mark. Grams. So I'm going from grams to grams. The whole course is going to be 3 steps. Molar mass of oxygen, then the mole ratio between oxygen and water, and then the molar mass of water. Okay, so we are ready to knock that out. Big old problem. Very exciting for us. I'm going to do it one step at a time, actually. Okay, so my given is 2.50 grams of O2. Now I'm all paranoid that I'm not going to write the same number over here. Oh my goodness. Okay. That means I need grams of oxygen on the bottom in my molar mass step. This is just simple oxygen, and there are 2 of them. So 16 times 2 means there is a molar mass of 32.00 grams in every 1 oxygen molecule. Boom, boom. I am now at moles of oxygen. We need to use the mole ratio. Woohoo! It is a 1:2 ratio between these 2 things, but I need to write the 1 on the bottom because that represents the given substance, the oxygen part. And then we are going to grant the moles of my ending substance, which is water, the 2 moles of water. Doing that, I am now out of moles. I've now made it to moles of my ending guy, but I am not done. The question asks you to take it to grams. That's the molar mass of just my water. We are ready with just our red color right now to use the molar mass, which says in every 1 mole, I have a certain amount of grams. Yes, putting the moles part on bottom so I can cancel that moles off and get 2 grams. I didn't even fill in my molar mass of water. Here we go. Hydrogen, 1.01. There are 2 of them, times 2. And then oxygen, which is just 16. So the molar mass of water is 18.02. Okay, now I'm ready to calculate everything up together. I go 2.5 times 2, and then times 18.02. 18.02, not 1, 2. And then the only thing I have is to divide on the bottom by 32. Amazing. Okay, so here's my answer. How many sig figs am I going to round it to? That's 3 sig figs, so my answer needs to be 3 sig figs. So this rounded to 3 sig figs is going to be 2.82. What are the units? Grams. And of who? Water. Cool. All right, last example. It says lead 2 nitrate. She didn't even give me an equation. What am I possibly to do? Well, you have to write an equation. What reactants are they giving you here? Well, it says lead 2 nitrate reacts with. So lead 2 nitrate is my first reactant. Reacts with sodium chloride. Lead 2 nitrate, sodium chloride. Those are my 2 reactants. Both of them are compounds, which means I need to be able to construct a formula for you. So that 2 in parentheses means that lead has, oh, you didn't even see the problem. That lead has a +2 charge. Nitrate, ooh, she's doing a lot with this one, is a polyatomic ion. Remember, nitrate polyatomic ion is NO3 with a -1 charge. Where is he? NO3 with a -1 charge, yes? So the crisscross, utilizing those parentheses around my polyatomic ions for lead 2 nitrate is I have a PB NO3 2. So that's my first formula. My second formula is sodium chloride. Plain old sodium, +1 charge, plain old chlorine, -1 charge. My formula for sodium chloride is NaCl. Amazing. And they tell you how many produce. Okay, Yes, I know one of my products is sodium nitrate. Let's see if I can prove to you that one of the products would be sodium nitrate, because I have a smart brain and I know what to do with these reactants. They are both couples, a couple between lead and nitrate, and a couple between sodium and chlorine. This is a double replacement reaction where they're going to be swapping partners. So lead cation is going to pair up with the anion from the opposite, the chlorine. And then the sodium cation is going to pair up with the anion from the other compound, the nitrate. Okay, so keeping in mind what charges we knew, lead and chlorine with a +2 and a -1 charge is going to write the formula PbCl2. And then my new couple between sodium and nitrate is what I'm going to write next as my second couple. Sodium had a +1 charge, nitrate still has a -1 charge, making sure the cation, the positive guy, is written first. So my formula for sodium nitrate is NaNO3. Parentheses are not required if you only have one of a polyatomic ion, but it sure makes things a lot easier to balance, so I'm going to keep it there. Keeping in mind when we write our own reaction equations, I do not bring any subscripts on over. I start writing my formulas from scratch with the two elements that I have, and depending on what their charge is, I create a brand new formula. I balance at the end. Okay, here we go. So I got to put a 2 in front of sodium chloride. Yes? And then I got to put a 2 in front of sodium nitrate, and then I think I am balanced. Whew, that's a lot of work. Now we get to finally read the ding-dang problem. What did they give me? What did they give me? What did they produce? I see the number, 85.25 grams. That is my starting amount. 85.25 grams of who? Sodium nitrate. Who is sodium nitrate? That guy. So here's my given, 85.25 grams. I know I'm going to use that eventually. Next up. What are they asking me to solve for? How many grams of lead-2 nitrate? Ooh, where's lead-2 nitrate? Is that guy, right? Okay, so underneath him, I'm going to write question mark grams, and I'll be using his coefficient for my mole ratio step. Grams to grams, I'm going all the way across. Molar mass, mole ratio, molar mass, okay? Oh, I know this problem is going to be a long problem. We got lots of space. Okay. So my given is this guy. First of all, let me set up my first step. So I have 85.25 grams of who? Sodium nitrate, NaNO3, right? And then I know that I've got to convert this guy to moles using the molar mass, which says, oh, there's a certain amount of grams of sodium nitrate for every mole of sodium nitrate. Whew. Okay, yes, I type on my calculator. I'm getting excited. Let's see. Sodium has a molar mass of 22.99. There's one of him. Then I got nitrogen, has a molar mass of 14.01. There's one of him. And then oxygen has a molar mass of 16. There are 3 of him. So I get 85 exactly, which is really exciting. So 85.00 grams. The purpose of this was for me to get out of grams of my given to moles of my given. We are at moles of our given. We are ready to cross over to the dotted line. We are ready for the mole ratio. For every 2 of my givens sodium nitrate, or 2 moles of my givens sodium nitrate, I have 1 mole of my ending substances, lead-2 nitrate. Boom, boom. I told you I didn't make my thing long enough. So we've now jumped over to the dotted line. We are at moles of our ending guy, but what we are not at yet is where we wanted to get to. We wanted to take it to grams. That's fine. Just convert that guy to mass using the molar mass, right? But for the molar mass, I need to see the 1 mole, of Pb. See, I almost messed up. NO3 too. For the certain amount of grams that are in Pb NO3 2. Amazing. Okay, so now we got to do a lot of elements here. Lead's molar mass is 207. I've lost him. Here he is. 2. There's only 1 of him. My next element that I have in here is nitrogen. Careful. How many nitrogens do you have? That 2 gets distributed to everybody on the inside. So I've got 2 nitrogens, so 14 times 2. My next element is oxygen. How many oxygens do you have? 3 times 2 with those subscripts gives you 6. So my molar mass for lead 2 nitrate is 331.22 grams in every 1 mole. 331.22 grams in every 1 mole. The purpose of this step was so that I can get out of moles of my ending and get to grams of my ending substance. Okay, so calculator, you're about to do a lot here for us. We have 85.25 times 331.22. Yes? So that's all the top stuff. And there's a couple of things in the bottom. You're divided by 85 and then divide again by 2. And there are a few other options on how you want to navigate this math in your calculator, but I like to just kind of divide by the things on the bottom, like one at a time. It makes me feel good, whatever. All right, so this is my answer. How many sig figs though? That number's got 4 sig figs, so my answer has to have 4 sig figs. So I get 166, and the last figure I need is, it's going to be a 1 now. And the units for it are the only thing I've not canceled off, which is grams of lead to, woo, I'm running out, thank you, I'm a hole punch, of lead 2 nitrate. Okay, so that's not, hopefully the colors, that's not too terrible, right? Hopefully the colors actually help a little bit. I feel like they do, especially when you're getting started. And if you want to use red and green colored pencils on tests and quizzes, like I can't, why would I say no to that? That sounds fine, but you probably will get to the point where you don't need that. But this is such a useful strategy for us being able to, depending on what I've given you information about, you can tell me information about somebody else in that chemical equation. So this is the heartbeat of chemistry. This is stoichiometry. We have done it, you guys. I've given you a ton of practice. And yes, we will do all the practice because chem is try. And so we will try and try and try until this just becomes a skill that is ingrained in our bones.